Hello everyone, welcome back. Today's video is on flooding. The learning outcomes of today's video are to define flood characteristics. We're going to define flash floods. And then finally, we're going to analyze real-life stream data from the San Lorenzo River and develop a flood frequency curve to try and calculate and predict when a 100-year flood will occur, or the size of a 100-year flood, I should say. A flood, the definition of a flood is when a stream overflows its banks. We have a stream that has a certain cross-sectional area. It can only take so much water. And so when that input of water exceeds the sort of volume of that stream, it will overflow to accommodate the extra water. And this is influenced by the soil characteristics of that stream and the topography of the region. The soil characteristics are dependent on porosity and permeability. Now, the porosity of soil is how much void space is in a given volume. So for every little grain of sand in a little area, there is a certain amount of void space, and that is porosity. A high porosity has a high amount of void space, and a low porosity soil has a low amount of pore space. So which one do you think is going to be better equipped at taking in more water? Well, that's a high porosity soil. One that's going to cause more flooding is a low porosity soil because it just can't accept a large amount of water. And so it's going to cause all that water that is applied to the soil to just rush right off. The permeability gets into sort of the chemical ability of soil to take on water. Soil that's extremely dry is going to be more resistant to take on water and accept water than soil that's already moist or wet. And then that also has an impact on the chemical formula. Are there clays? Those will swell and absorb more water. And so these soil characteristics will tell you which regions are more likely to have flooding. And also the topography, that is the slope and shape of our surface elevation. Regions that are more valley-like are also going to be more prevalently more prone to flooding. Some lingo you should get familiar with of floods is the stage of a river. It doesn't need to be a flood, but a stage of a stream or river is the elevation of the water surface. So this is measured in distance, usually in feet in the United States. And that can be like 5 feet, 10 feet. And that stage, that height is directly proportional to the amount of water flowing through that area, that cross-sectional area, because the cross-section of the river is not changing. The height of it is changing a little bit. So there is a little increase in area, but based off of our understanding and study of that cross-sectional area, we can take that surface elevation and directly correlate it to a discharge, which is measured in volume per time. So usually that's cubic feet per second, CFS. Upstream floods are floods that affect small localized areas, and those occur primarily in upstream of river areas. That's because when floods occur, when rivers start to get down to where they enter a larger body, enter the ocean, they get a lot more gradual and they widen out into floodplains and deltas. And so when those downstream floods occur, these are floods that are going to affect a much larger area than the head of that river, which was in the mountains. Those mountain creeks are going to affect maybe a channel. It'll affect maybe a road that's right on that river. It's not going to affect people who live higher up in the mountains because the area is so much more confined, and that's due to the river flow and its ability to erode those regions, as we talked about in our previous video. And so some more on that. Flash floods are a type of upstream flood, and these are defined by just a pretty rapid increase in the stage of a stream or river. And this is sped up by flowing through canyons and really steep-sided valleys. You get a lot of rain on the top of a mountain, and then it's basically channeled like a funnel through through entire ecosystems and causing flash flood in a region. And this is really common in deserts. Deserts have things called ephemeral streams, which are very, very temporary streams that maybe even flow once a year, if not between multiple years. And these are very prone to flash flooding. They by definition are going to flow with extreme intensity very infrequently. And in the desert, people like to hike in these beautiful slot canyons that have been carved out by the flow of water over hundreds of thousands of years. And these flash floods can occur so suddenly that they'll take hikers and people who are in these slot canyons with them. An interesting thing too to note is that the rain and the porosity of the soil basically pushes all the water downstream. There is no uptake of water into this very low permeable soil. And so you can have rain that's really, 100 miles away from where you are in the desert, and then you can have an instantaneous flash flood. And so it can be difficult to know what weather conditions where are going to impact where you're at in that moment. And so it's best to avoid regions like that because they are prone to flash flooding. So all streams, you can plot their stage or discharge over time and develop a figure called a hydrograph. This is a hydrograph of the San Lorenzo River for the last 3 days. The USGS monitors streams and rivers all across the country, and this is actually publicly accessible for you to look at and maybe do some data analysis with, which we're going to do in the next couple of slides. So I think that's pretty cool. If there is a big event happening, you'll see the stage increase very rapidly and die off really rapidly. That is a flood occurring because rain happens in a certain time frame, and then all of that sort of gets discharged. Your distance from that rain event, that input of water, is going to be directly correlated to sort of the steepness, the spread of that water over time. So you can imagine if you're really far away from a river or a rainstorm, that water is going to spread out over a longer and longer period of time. It's going to slow down the further away you are from that rainstorm because of the properties of a dendritic river system. And so that input of water is going to be less impactful downstream because your river as a whole is a lot larger and the discharge area is a lot larger. So it's not going to look as dramatic or be felt as impactfully as it is in the upstream region. And so downstream floods tend to be a lot larger than upstream floods as a result. And so flood frequency curves are how we calculate something you've heard as probably like 100-year flood or a 100-year storm. What does that mean exactly? That means this flood size has a 1/100th probability, a 1% probability of occurring in any given year. And this is all based on historical data. A lot of environmental systems, we're able to calculate probabilities of things occurring based off of historical data. If the last 10 years are like the next 10 years, then this is a great way to know what the next 10 years are like by looking at historical data. And so I want you to think about what things that are happening in our environment might affect that sort of philosophy, that assumption that our historical data is going to be like future data, and we can use it basically as a direct predictor of what we're going to experience in the future. And so a 100-year flood, a 50-year flood is a flood that will happen once, or it's a 1 in 50 ith probability that a flood will occur in any given year. And so we're basically inverting that and just talking about things in terms of 100-year floods. With global climate change, 100-year floods are going to be a lot more common. What that means is these large weather events, these large flooding events are going to become more frequent because of the increase in extreme weather events caused by global climate change. And so you basically calculate this by taking historical data. We're going to rank it from 1 to 50. We're going to turn that rank into a current reoccurrence interval, the interval in which that particular event will occur, and then we'll plot that reoccurrence interval to discharge and use that to predict what a 100-year flood will look like. So let me get out of my thing here. I have pulled stream data from the USGS for this site on the San Lorenzo River. I believe it's right before the downtown area. And they have all sorts of daily statistics, monthly statistics, annual statistics from 1953 to 2023 to this year. And so I want you to notice that this is not 100 years. So we're going to use 70 years of data to predict when a 100-year event will occur. And most monitoring sites were built in the last under 100 years. A lot of weather wasn't monitored before the 1900s. So this is something that will cause issues. The more data you have, the better you will be able to predict what is going to occur. And so I've taken this the discharge values from this point and input it into my R script here. I don't know if anyone's familiar with R, but basically I'm going to input it into a data frame. We can take a look at our data frame here. It basically has the peak day, the date at which that peak flow occurred, and then the maximum stream flow for an annual year. So we've taken the maximum stream flow felt by that given point for a whole year and isolated it in this table. And so here you can see it ends at 2021. Oh, there's some years represented twice. That should be okay. And there was some time off between the 60s and 1988. It doesn't need to be every single year, but we'll take all this data and use it to predict. We only have 43 data points here. And so we're going to order those stream flows from largest to smallest. And then we're going to rank them in a variable I called rank from 1 to 43. So number 1 is going to be our largest storm event, and number 43 is going to be our smallest. Then we're going to use that to calculate the reoccurrence interval. That's based off of the number of years I have represented, which is 43 years total. We're going to divide that by the rank that I've placed it under. So out of my 43 years of data, I've ranked each one from 1 to 43. And so based off of that data, my number 1 flood is going to be ranked. I'm going to calculate a reoccurrence interval of 43. And so I will plot that to our right. And so you can see here, this is that data ordered and plotted based off of reoccurrence interval. Like I said, we have 43 data points. And so our largest flood is going to be at 43 years, the largest reoccurrence interval. And so we can say the probability of that occurring on any given year of a 30,000 cubic foot per second stream flow discharge, the probability of that happening is 1 over 43, is 1/43. And it makes this nice logarithmic plot. And so I can actually take these 43 data points and make a linear model. This is a logarithmic plot, as I said. And so if I take the log of y and relate it to x, I can make a linear model and then calculate the volume I'd expect of a 100-year flood based on this data. And so that's where this 100 comes from. And so I'm going to do that now. And it's calculated that the probability of a 100-year flood is about 5 million cubic feet per second, which is very large, very large. And if I had more data points, that would become a bit more reasonable and probably lower down. But you can see some of the issues with what kind of data set you're using. And so I wanted to take a sample of 10 data points from that data set that we just worked with and see what happens if I only have 10 data points. What does my figure look like then? And so this one calculated a 100-year flood that has a volume of some astronomically large number. And the size of that predicted flood is about 60,000 times that of what we predicted with 43 data points. So we've only decreased our sample size by 4, but we've dramatically increase the sort of uncertainty of the value that we're calculating. And I'll make the plot of that here. So on this random sample size, we really only sampled those smaller, more likely events, and that 30,000 cubic foot per second flood event was not sampled in this little experiment. And so we're really overestimating because we just don't have data of a flood that size. And so in areas that are going to start experiencing a lot larger flooding events, this is going to be quite a problem, because we're basically looking at historical data that are all these small events. Climate change and certain external factors have changed the future, and we basically still have to use historical data to try and predict what is going to happen in the future. And so that's really complicated, and you can see how that causes issues. So more data is always better, and a 100-year flood is something that in some locations we don't even have enough data points to calculate the probability of a area without doing a little modeling, without doing a little linear forecasting. So flood frequency curves are really cool, I think, really valuable. And I also find it really interesting that this is something that you can go and do on your own if you are so inclined. Look at a stream gauge in your area and look at the historical data and try and calculate, like, what's the probability of what is the size of a 100-year flood. That concludes our video today. Please don't hesitate to reach out if you have any questions, and I will see you next time.